Welcome back to our discussion of light trapping in thin film solar cells. In the first part of our discussion, we looked at how the path length of light through an absorber layer can be increased without increasing the geometrical thickness of the absorber by using surface textures. We also discussed that smaller surface features more effectively scatter light with a shorter wavelength, while larger surface features more effectively scatter larger wavelength red and infrared light. We will now look into the effect of surface texture on the solar cell parameters. We will do this by comparing three microcrystalline silicon solar cells with differently textured substrates. The first has nano-sized features, the second cell has micro-sized features, and the final cell has a modulated surface texture, which means it has nano-sized features on top of micro-sized features. Since the goal of the surface roughness is to increase the light trapping in the cell, we will look at the JSC or short circuit current density of the cells first. The JSC of the microtextured cell, plotted here as a function of the absorber layer thickness, increases with increasing absorber layer thickness. The shape of the curve matches that of the Lambert-Beer law for absorption that we discussed in the first course of this program. The JSC of the nanotextured cell and the cell with the modulated surface texture, indicated by the red dots and blue squares respectively, is much higher for thin absorber layers. We can therefore understand that the nanotextured features are much more effective at scattering the incident light. The texturing features affect more than just the light trapping of the cell, however. We can see that the fill factor of the microtextured cell decreases with increasing absorber layer thickness. So does the VOC of the cell. This decrease is much more pronounced in the cells with nanotexture, especially in the cell with only nano-sized features. Since the nanotexture is effective at trapping light, these cells have a relatively high efficiency at a low absorber layer thickness, but the efficiency hardly increases for thicker absorber layers due to the poor fill factor and VOC. But why exactly do the surfaces with nanotextures have such a detrimental effect on the VOC and fill factor of the solar cell? The cross-sections of the solar cells provide some insight. This figure shows the microcrystalline silicon absorber deposited at the top of the micro-textured aluminium doped zinc oxide layer. The cell is covered by a metal electrode. Next, we consider the same absorber layer on top of the nano-textured TCO layer. Whereas the silicon on top of the micro-texture has grown relatively uniform, large cracks are present in the crystalline tissue on top of the nano-textured surface. The cracks or defective filaments are indicated by the yellow arrows. We can clearly see that the cracks occur in the valleys of the sharp, V-shaped nanotexture features of the TCO substrate. The larger, smooth, U-shaped microtexture features do not have these sharp valleys, and no large cracks appear in the material. Similar results can be observed for the modulated surface texture absorber. The cracks are zones of porous material that create shunting paths and strongly increase charge carrier recombination. The increased recombination and leakage current result in lower VOC and fill factor. The solar cell performance is directly related to the density of these defective filaments. Note that while here the results are shown for nanocrystalline silicon, achieving a device quality crack-free material on substrates with sharp features is generally very challenging for any PV material that contains a crystalline phase. Now in summary, we have discussed that light trapping for the various spectral ranges requires specific adjustments to the typical feature sizes used. Nanoscale textures should be applied for effective scattering of the blue and green light, while microscale textures should be used for infrared scattering. Modulated surface textures need to be adapted to achieve effective scattering of a broad spectral range. Finally, we discussed the relation between sharp substrate features, the formation of defective filaments, and their effect on solar cell performance. In the next video, we will introduce other important concepts in photovoltaics, namely multi-junction solar cells.